So much for that introduction and the opportunity to speak today. I, I think that the two talks you're hearing are linked nicely. Um, I'm going to tell you about a project we have that's dedicated to being the observational ground truth for the ideas that you just heard in Allie's talk. So, what we set out to think about was how you might support with atmospheric observations the evaluation of policy on a timescale at which the policy could be refined, and so to give direct feedback on sort of electoral timescales, if you like. Um, and so you see here an image of San Francisco, and just to give you a flavor of the kind of question we were asking is, can we tell with observations how the emissions are different in that downtown area from the area half a mile away that's 2- and 3-story buildings and some homes, some office space. So that's the sense that we mean by neighborhood resolution. Can we understand how emissions are varying on the sort of 1 kilometer space? So yeah, that next slide is fine now. This sort of gives you a sense of the questions, and very much aligned with what you just heard. We're interested in these questions about the intersection of greenhouse gas emission controls and air quality. So starting with what can atmospheric scientists do with observations that support cities' evaluation of their successes in emission reductions? And also, if we think about how the incentives might work for cities to take action, there are lots of strategies that talk about commercial entities entering into some form of cap and trade program. Very few strategies that think of how cities might engage in that. And so what observations might support entry of cities into the permitting that would allow them to reduce their emissions? So you could imagine that atmospheric observations would say that an urban policy is reducing CO2 emissions by X, and that an industrial group could buy those permits from the city, so they're allowed to emit for a little bit longer as we find a strategy towards net zero. And then in synergy with that, in many cities, ozone is not improving as fast as we would like. We'd like to understand options that put us back on a better path. And we've just heard in Allie's last slide about inequity and pollution in different neighborhoods associated with industry and traffic in the US that's almost entirely transportation related to trucking and other sorts of goods movement. So in the next slide. So here's just one example of a plan. So I live in the city of Oakland. It's one city over from the city of Berkeley. In the metropolitan area of the San Francisco Bay Area, there's about 9 million people. The city of Oakland is about 500,000. And you see here the greenhouse gas reduction plan. The red dotted line is the actions that are under state control. So the state of California will issue policy that will have those effects. And then if we want to get to net zero, the city has to do its part. And so you see that green dotted line is the added benefit of the city's individual actions. And that red circle up top, or oval, gives you a sense of where the city of Oakland is across the bay from San Francisco on the other side. So that's just to put context that cities have a significant impact on how the greenhouse gas emissions will play out. If we go to the next slide. So this is work from Kevin Gurney at Northern Arizona University in a paper this year. And what Kevin did was prepare a uniform model for greenhouse gas emissions in 50 cities in the United States. And then he, city by city, pulled their own greenhouse gas inventory and compared them to that one uniform strategy. And what you see in this is that in some places, the cities agree with his assessment of greenhouse gas emissions in a uniform strategy. And this is not to say, and he would tell you that, not to say that his assessment is correct, but just to show you how difficult it is to get an answer that's identical to a uniform strategy. So some cities have a factor of 2 or 2.5 different, plus 150% relative to the uniform strategy. Some cities are right on. And then if you go into the detail, even the cities that agree, if you look sector by sector, they don't agree. So we don't yet have a strategy that allows cities to all be on the same basis when they're reporting and thinking about their greenhouse gas emissions. So that's a place where we believe atmospheric observations can really support cities, is by directly helping them quantify what's going on within their boundaries. So the next slide. So the strategy we built was an observing strategy that we call Beacon. It's an air quality and CO2 observing network. The sensors are located everywhere you see a green dot here. So there's about 70 of them in the San Francisco Bay Area. And you could hop over to that website and see some examples of what's happening. It's in near real time. So the observations from the last hour or two are probably there. If you go, most of those sensors are located on the rooftops of schools and museums. And in a parallel part of this project, we are working on science education with teachers in those schools. So in the next slide. So in each of those sensors, it looks like this inside. There's 4 of the alpha sense electrochemical sensors measuring air quality gases, CO, ozone, NO, NO2. There's 2 particle sensors, one by a Shinyake and one a Plantower. Plantower is the sensor that's inside of purple air. You might be familiar with that. And then a CO2 sensor from Vaisala. So it's a packaging of available commercial instruments and deliberately linking CO2 and the air quality gases, because pretty much anytime you emit an air quality gas, you're doing it by burning something. And so there's almost always CO2 emitted. And although, as we heard in the last talk, the greenhouse gas inventories and the air quality inventories are built entirely separately and by separate agencies here in the United States as well, that doesn't make very much sense, because the emissions are grams of some pollutant per gram of activity, and per gram of fuel burned, and the gram of fuel burned is CO2. So we should be building models and inventories for the 2 kinds of gases in the same breath. There's no pointless to separate them and creating more work for everyone. So in the next slide. So, and having 70 instruments, or now we have over 100 out in the field, presents a significant calibration challenge. You can't conveniently bring a cylinder of standards on the rooftops of schools. That would add a logistical burden that's unreasonable. So we've spent a lot of time thinking about how you maintain an accurate and precise calibration over time at locations without bringing standards to every location. So we have a single reference location within the domain, and then a set of strategies that allow us to think about the network as a whole as an instrument, and use both meteorological moments when all the sensors should be seeing the same thing, and various ways of tracking the background that allow us to keep the calibration precise and accurate over long times. So for CO2, that gets us to about 1 part per million accuracy. Recall there's about 400 or so parts per million CO2 in the atmosphere, so that's a part in 400 precision. Next slide. So here are the things that we'd like to learn. We'd like to be able to track trends over time. We'd like to be able to assess emissions by individual sectors in aggregate over the city. We'd like to be able to create a map of emissions and exposure for understanding environmental justice and equity. And then we'd like to be able to do process studies. So, for example, can we, if you're going at nominal mid speeds vehicles are most fuel efficient. Slower or faster, they're less fuel efficient. So we'd like to be able to validate models of emissions versus speed in the real world fleet, as distinct from the emission models are now built up for performance on a dynamometer or theoretical performance of individual cars, but we don't know how that is performing out in the real world. Similarly, catalytic converters work incredibly effectively when they're hot, so that right now we're expecting a large fraction of the NOx and CO from gasoline-powered vehicles in the United States come in the first 10 minutes of morning driving. And that's an enormously different spatial pattern than in any of the models. And then cars in the US are mostly gasoline, trucks are diesel. Either way, the trucks are much heavier, so their mix of emissions between cars and trucks are quite different. So all of those things are things we'd like to be able to tease out from an observational network with direct inference from those observations somehow. So in the next few slides, I'll try and give you some examples of how we go about this. So next slide. So in one example, we can look at the amount of CO2 in the atmosphere. And if we pull out the weather variables, there's a very strong correlation between the excess CO2 at any of the 70 sites in our network and the number of vehicles per unit time on the highway. And so that correlation you see on the left for one example site, that's one that's closer to the highway. And then you can take the slope of that correlation and plot that versus distance from the highway, and you see there's a strong decay in that correlation. But that it's got a characteristic shape, and that shape is of a Gaussian plume emitted from a line source. So if we gather that analysis and fit that shape, we can do a pretty good job on getting the annual emissions per vehicle for the average vehicle on the road. And then in the next slide. So here we see the 3 years of the normalized emissions as inferred in that way. This is CO2 emissions per vehicle. And we see there was about a 7.5% decline in emissions over these 3 years in the observation, as determined directly from the observations, and a model gives about 2.3. Those two are within the uncertainty of each other, but we believe that within a couple more years, or as if we add additional sensors to our network, especially ones close to the highways, we'll be able to tell the difference between these two, and whether that difference is because relative to the model, there's been more penetration of electric vehicles into this community, or whether the observations, it's just noise in this initial assessment of the observations. Next slide. So the other example I'll show you is as a mapping example. So we looked at the 6 weeks before and after the COVID-19 shelter in place in this paper from about a year ago. And this is work done by Alex Turner, who was a postdoc with me and is now a professor at the University of Washington. So in the next slide. So the way we go about this is there's an inventory that's mapped at 1 kilometer. That inventory you can think of as a prediction or a hypothesis about the structure of emissions in space and time. And we convolve that with the weather to get a forecast of what we should see at every location in this network. Then we have the observations at all the locations in the network. And what we're going to do is some form of an inverse model that's a synthesis and iterative improvement on the prediction hypothesis. So it uses as a base case an a priori, in this language of the inversion, what we already know about emissions, and then we're trying to get a better field. So next slide. So here are the observations. We'll use that purple set, which is 6 weeks before the COVID-19 shelter in place, and the green 6 weeks after. And we'll compare those two. And you'll recall that this happened right at springtime. So there's changes that result both from changes in human behavior and changes from the weather. And so we need this weather model to disentangle those two. So the next slide. So here's just the average over the entire domain of our observations. Here's the CO2 averaging 6 Sundays before, 6 Sundays after, and so on for the other days of the week. You can see there were quite large changes in morning rush hour behavior. Emissions are much lower. You can see the changes on the weekend are fractionally much smaller. Next slide. So here we just insert large amounts of computer time trying to solve a fairly massive matrix problem of hours of observations and then hours of the model. Next slide. I think we skipped one really quickly. So there was this one. So here's the results on a map. So the inventory of CO2 emissions in tons of carbon per square kilometer per hour. You can see the high emissions on the road network, especially at the choke points feeding the San Francisco-Oakland Bay Bridge that carries traffic between the two cities at rush hour in the morning. And then you can see that during the shelter in place, the primary changes are along those highways that feed that bridge. And then in locations that feed other major transit points within the Bay Area. So bridges in the north of that domain, and the black line you see here is the place where our observations constrain emissions best, and then outside that we constrain them worse or less, so we revert to our initial guess more or less. And you can see that there's over this period there was a lot of growth in the biosphere, and that's showing up as green negative emissions. So those are places where carbon was being taken out of the atmosphere and green plants were growing during this time. Next slide. So if we add up all those changes, here you can see a before and after for 3 sectors. The sector of vehicles on the highways, all other anthropogenic, both industrial and non-highway driving and home heating, and then the biosphere. And that red line is to guide your eye, so that before the shelter in place, most of the time we were over 400 tons per carbon hour over this region. And after the shelter in place, we were mostly less than that. And you see the biggest changes are in this orange trace, that's the vehicles. So it's a 25% integrated reduction in the total CO2 emissions, and it was a 45% reduction in vehicle-related emissions. And those happened at differentially on the different days. The emissions on the weekend changed hardly at all. Emissions during the week of people going to work changed dramatically. Next slide. So of course, we didn't just change the CO2 emissions. Along with the CO2 emissions come all the air quality gases. So here's on the top, the CO2 emission, CO2 concentration changes I just showed you. On the bottom, the carbon monoxide changes. And so you see those here in the same color scheme, blue for before, orange for after. So pretty significant drops in the carbon monoxide concentrations. And then next slide. And we've done the same sort of inverse modeling to get carbon monoxide emissions. And here we can see that similarly, the traffic-related CO emissions decreased quite a bit from this period. Okay, next slide. So we're excited about this as a strategy for thinking about getting at emissions, mapping them, doing this at the neighborhood scale. In addition to the Bay Area, we have 10 or 12 measurement locations in the city of Los Angeles in a collaboration with Will Barrelson at USC. We have 10 nodes out right now in Glasgow, and we're hoping to have 25 by the time of COP26 next month. The others are on the ground waiting for permission for installation. We just shipped another 10 to Leicester, working with Hartmut-Busch, and we're in conversations with collaborators in a variety of other cities, looking for ways that we can bring this technology and strategies for analysis to a larger number of cities through cooperation with other scientists. So next slide. So just to sum up what I've told you about today, we've demonstrated that there can be quite rapid reporting of CO2 emissions. So observations from May 2020 appear in a peer-reviewed scientific publication in November 2020. And that's important because if we're going to give feedback to policymakers, if we have to do the normal scientific strategy of making improvements in our understanding of emissions on 10 years, there's an entirely new set of elected officials in charge on that timescale. So we want to be able to give feedback on policy on the timescale that's relevant to the individuals who created that policy, so they can see the positive effects of their work and to understand where things are changing in the way they planned and where they're not, and so they can adjust. Showed you that we can detect 25% changes in emissions with just 12 weeks of observations, and that we can detect 3% per year or so changes using analysis focusing on correlations with vehicle number in the fuel efficiency of cars. And that we can do things that talk about attributing emissions by sector within cities. We can show, we have timing information about when in the day and which day of week emissions have changed. So daytime change differently than night, weekends change differently than weekdays. We have a paper I didn't tell you about looking at speed and fuel efficiency. It's posted on ACPD now. The first author is my student Helen Fitzmaurice. And I showed you just a hint of the air quality work that we're beginning, where CO gives us information about emissions. And what I didn't show you is that the time of day changes indicate that emissions are higher and spatially mapped differently when vehicle catalysts are cold. So the morning map looks quite different than the afternoon map. So in the next slide. So let me thank you for your attention and thank the incredible team of postdocs and students and staff who've worked with me on this project, and turn it back to you in the audience for questions to me and Ali and for discussion this morning.